I feel shy after that introduction. Thank you, Cecilia. Thank you everybody for coming today and to help me share these ideas about building bridges towards some generative embodied artificial intelligence. So the theme today is about building bridges, and there will be 3 bridges in this talk, and I'll kind of point them out as we go along. So my group is called the Collaborative Learning and Adaptive Robots Group, CLEAR and US, and we're driven by problems. Okay, we're driven by problems in assistive robotics, so I'm interested in helping robots help people. Okay, I'm particularly people with disabilities as well as the elderly, so tasks like room cleaning as well as assistive feeding. These problems are hard because they involve both physical interaction as well as social interaction. But I'm becoming a little bit more optimistic recently. And my optimism is really driven by 2 large trends. And I think that everyone here has seen these 2 trends. The first is that our robots are getting better and they're getting cheaper. And this was taken at ICRA last year in London. And if you walk around ICRA today, you can see lots of similar robots as well as lots of humanoids. Okay, I've seeing a lot more humanoids now. So we're getting better and better robots. And these robots are really much better than I would have expected when I was a PhD student. So I'm very surprised by this, and I feel very, very optimistic. One thing to note, however, is that these robots are mainly teleoperated. So getting a fully autonomous system is still extremely challenging. So that brings me to the second trend, and the other trend that everyone knows about, which is about generative AI. So we see tremendous improvements in the types of data, type of content that these models can generate based on ingesting a large amounts of internet scale data. So on the left, it's a completely AI generated video of a bird. It is generated via Sora, which is a diffusion model. On the right, of course, is ChatGPT, and everyone here has played with ChatGPT, either for fun or maybe to help you to refine your papers, right? Okay, so we have these two kind of developments, and with these generative models, I think it doesn't take you too long playing with them to realize that they have faults. Okay, and one of the biggest faults is that they don't really have a core understanding of our physical world. So if you generate images using Sora, for example, or Midjourney, or these diffusion models, you can get very weird looking images that violate what we know as physics. Okay, and this shows that these models don't really have a core understanding there. So we have these 2 worlds. We have this world where we live in with our robots, okay, our physical world. And on the other side, we have this world of generative modeling. And I would like to try to bridge this to some degree. So the talk today is going to be about this kind of bridging, and I've split the talk into 2 parts, okay? The first part is about taking some ideas from the generative modeling land to help us over here in robotics. And I'm going to use diffusion, but with a little bit of a twist. And this little twist will allow us to take ideas from robotics and put that into diffusion, okay? We'll see how that works. And the second part is kind of walking in the other direction, where we're going to take some things that we developed in robotics, particularly tactile sensing and tactile perception, and then we're going to help these LLMs to gain some physical understanding of the world. Okay, so that's what I want to talk about today. Now, this work is really the work of my wonderful students, okay, and I would like to thank them up front, as well as my funding agencies and my wonderful collaborators as well. Okay, so let's get started with the first part. So I think by now you know of this diffusion-based policy learning. So this is the application of diffusion models towards learning policy. So you can generate action sequences, you can use it for navigation as well as for manipulation. And what I want to do in the first part is to open up this box a little bit, okay? I'm not going to shy away for some math. There will be some math, I'm sorry. But I want us to gain a good understanding of how these models work, because we're going to change it in some way. And kind of seeing what goes on inside allows you to appreciate this change, all right? Okay, so diffusion models. We want to be able to sample from some distribution, okay, of trajectories, all right? And this is hard, okay? So what we can do easily is to sample from some simple analytical distribution like a Gaussian, all right? So we take this Gaussian, and then we change this Gaussian gradually, or we train a model to change this Gaussian to the nice clean trajectory that we want, okay? So this model that changes this action sequence from a Gaussian, this random action sequence into something clean, this is our generative model. Unfortunately, if you try to train these things from scratch, this is where the P complains, okay? He's like, this is too hard. I don't know how to do this, okay? It's very hard to take this messy, trajectory and transform it into something clean. This is like giving you a PhD student, a messy idea at the beginning and say, write me a thesis, right? It's hard to do. And they start crying. So as an advisor, you give them a little bit of help. So you guide them along the process, okay? That's where we introduce a variational distribution. I'm gonna help them out. And basically, I construct them a path, okay, towards getting their thesis, and I work backwards. All right, so this is easy to construct in diffusion land. What you do is you take your clean signal, and then you gradually corrupt it with little bits of noise. And if you can do this long enough, then you're going to get this messy trajectory at the end. Okay, so that's the idea. Once you do this, you can train the model. There is a particular challenge, however, which is inference time. So when you want to generate a nice clean signal, you have to first sample this noisy trajectory and then gradually change it all the way to your action trajectory. And if you run this in practice, typically you might see something like this, where, depending on how long you perform your inference, performance goes up. All right, but you need to run it for a sufficiently long time, or your action distributions will be fairly messy. What we like to do is to try and get a better performance versus cost trade-off. So we want to push this curve. All right, so we can get better performance with less inference time. Okay, that's what we want to do, because we don't want our robots to be, kind of taking an action sequence, pausing for a long time, and then continue the action sequence. This is not something we would like to do. Okay, so this is our model. This is diffusion models. We have a particular challenge here. Can we fix this? So let's look at our model. Let's try to think about, what can I change here? So one key idea that we have proposed is to say, hey, let's not start from Gaussian. Okay, let's start from something a little bit more informative. Let's use something that we know about in robotics. So once you free yourself from the shackles of Gaussian, you can start to do interesting things. Okay, you can start to use a handcrafted or heuristic distribution, something you can use a motion planner, or use a simple heuristic in order to craft your initial trajectory. You could use a data-driven model. You could learn something in simulation and then train it with little amounts of real-world data. You could train it based, start with a related task, a policy for a related task. Or you could use something from foundation model. You get, ChatGPT to output something, and then you start from there. Okay, you don't start from scratch. And then I'll leave it to your imagination to think of other kinds of source distributions. So I could sample something. So here's a simple, instead of a messy thing, I start with a straight line. Okay, that's what I start off with. Okay, I want to learn this curvy line. There is a little problem. Okay, so what's the problem? Anyone see the problem? The problem was my guide. Okay, remember what I said? How did I construct my guide? I said I'm going to start with my clean thing, and then I'm going to gradually add noise. Okay, and sorry, if I gradually add noise to this, I'm not going to get a straight line at the end. This is not going to work. This guide is wrong. Okay, so I'm going to have to change my guide, and for this work, we use something called interpolance. It's a very simple idea. You basically blend, okay, your source, your sample from your source, and your sample from your target. Okay, that's a very simple idea, and this can be easily constructed. Blend it with some noise. So this is the equation. The equation is very simple, actually. If your k is 0, so you're somewhere here, okay, your k is 0, then this becomes just a0, the rest of the terms drop off. So you get exactly, the sample here. If it's, if k is equals to large k, small k equals to large k, then you only have this sample left, this term left, everything else drops off, okay? And then in the middle, you have stuff that blends the two samples together. Okay, so that's the key idea. All right, we encapsulated this in a model we call Bridger. And Bridger allows you to bridge arbitrary densities. All right, and that's our second bridge. Okay. It's a little bit different from the key ideas that I shared before because it's in continuous time, but the basic stuff is all there. All right. Because it's in continuous time, you have a stochastic differential equation, but when you solve it, also you discretize and you solve. All right. Training is very much like diffusion models, so you just train using a squared loss, and you get out these velocities that you can use to refine samples or get samples out. Okay, so in the paper we also described some theoretical results to actually say why source policies work. Here I'll just show you pictorially. Okay, so let's imagine that this is our true target. Oh wait, let me see. Okay, this is our true target. Okay, this is what we want to sample. Okay, the distribution that we want to sample, and we start off with Gaussian. Now, you start with Gaussian. If you just solve it for like 5 steps, you don't get something really good. If you start with something a little bit better, then you can see these two things are much closer now, just in 5 diffusion steps. And if you start with something even better, then, well, this is pretty close. Okay, so there's some synthetic results. Does it actually transfer over to robotics? And it does. So this is grasping, 6-DoF grasping. This is SE3, state-of-the-art diffusion model, okay? Starting from Gaussian. Diffuse for 10 time steps. This is what you see, not very good. If you start with something a little bit better, let's say a VAE trained model, you get much better grasps, just using 10 diffusion steps. This is a simple heuristic policy. What's the heuristic policy? It's super simple. You find the centroid of that object, you just randomly generate grasps that point towards the center, and that's the heuristic. And even with that heuristic, you get something really, really, really good. Okay, then we ran this on some robots. And guess what? This is the baseline. This is actually 3. It doesn't perform very well with very few diffusion steps. This is 5, k equals to 5. This is Bridger using our heuristic policy as a source. And for this, in this case, it successfully does it. Now, remember I showed you this graph right at the beginning. This is not a cartoon. It's the actual data that we get from running our models. So we can go from something like SE3 diffusion and really push up this towards something much better. So you're getting much better trade-offs between your inference time and performance. So with 10 or 20 diffusion steps, you can see here you're above 80%. Okay. We tried something a little bit more complex. This is operating a shadow light hand in order to do a synthetic wound cleaning task. So I talked about wound cleaning at the beginning. So what Kai-Chi is showing here, so my student Kai-Chi let this work. He's kind of showing the robot starts off with a hand in some random position above the sponge, and he has to pick up the sponge and then clean off a mark on the synthetic human tissue. And so Kai-Chi is just showing the demonstration over here. We don't have a fancy teleoperation setup, so we did it via kinesthetic teaching. This is very tiring. You can see Kai-Chi is like exhausted by the time he finishes these things. He's like, not easy. Like I said, I work with wonderful PhD students who are willing to do all these things. Okay, so this is a baseline diffusion policy. It's running on 5 diffusion steps. And I want you to pay attention to the fingers. Okay, look at the fingers here. You see a lot more jerky movements because we're not diffusing for long enough. Okay, and you can see that it doesn't really perform very well for this task. Okay, this is our Bridger method using a heuristic. The heuristic is just one of the trajectories. Okay, and I should mention that in this case, I said before, the initial position is randomized, but the mark is also randomized across the synthetic human tissue. Okay. So we see overall much better performance, okay, especially with the low number of diffusion steps. You can see here significantly better performance just using this idea of let's not start from Gaussian. Okay, that's the key idea. Okay, so there's some takeaways. Don't be shackled by Gaussians. You can actually start off with other distributions. It's nice because I think it allows you to make use of existing information or knowledge when they're available. You don't have to use them. You can use the Gaussian if you want, okay? With a rich policy class. So the nice thing about these diffusion models is that they're data-driven. They allow you to output, continuous actions, and you can represent multimodal distributions, which is really cool. You get a better performance versus time trade-off. I didn't show any slides about this, but in the paper, we also talk about data trade-off. So you actually are able to do this with much less data. So I think, yeah, it works because you're getting the best of both worlds. You're using existing models or existing policies to support performance when your data is little, but you can scale with data as well. And there's a lot of room to expand and explore. So we've tried out actually different kinds of interpolants. I showed you some stuff with linear interpolants, but you can actually use non-linear interpolants as well, and you can get better performance if you use some sorts of non-linear interpolants. You can try out different sources. I've kind of showed you simple sources, but you can take stuff from a foundation model. So if you're interested in doing stuff like that, please let me know. I'm interested to collaborate. I think from a scientific perspective, we should try to understand a little bit what's going on under the hood with respect to the inductive biases that we are putting into this model. You can think of the source policy if it is an inductive bias. And what's going on there, which especially with respect to robustness, is something that we should study further. And these elements of transfer. So when does positive transfer happen? When does a negative transfer happen? This is some things that we really need to figure out. Now this framework of kind of generation and refinement, we've been kind of doing for a while, right? You can think of it as sampling from some source distribution and refining it, okay, in order to get to the target. It started off with Fatir, and we were kind of refining stuff from GANs, and then TAS, then did this with multi-criteria grasping, and now Kai-Chi has really taken it further and applied it with diffusion models. And I'll just point out that Tas and Kai-Chi are on the job market, so if you want amazing robotics AI people, let me know, okay? Okay, so let me move on to the second part, and the second part is about giving LLMs the sense of touch. Okay? And in my group, we've been working with touch for a while now on tactile perception. We work on stuff with direct physical contact with the object. So when your tactile sensors are in direct physical contact with the object, can I tell whether it's hard or soft and things like that? Also with indirect physical contact, so through a tool. All right? So if I'm using a fork, can I tell what I'm prodding? Where does the contact happen? We've also done things like that. On the other side of the land, right, we have these beautiful multimodal models, okay, that accept different kinds of input, different kinds of sensors. So I think many of you gotten this, right? This nice spread, this nice piece of cloth as a ICRA participant. And there are many ways you can describe this to a large language model, right? To a multimodal model. You can, put in text, or you can use vision, show a picture of it, or you can use audio. We are interested in touch. So this is a gel site sensor. Right, this is off-the-shelf tactile sensor that you can buy, all right? And you can apply it to the object in order to see the different kinds of textures that emerge, okay? And from there, if you have one of these, you should touch it and feel it, okay? It's a little bit rough, yet it's pliable and deformable, okay? And I think that this modality is really important for giving these models an understanding of the world. So we're trying to do some sort of physical grounding to language, right? So what does it mean to be soft? What does it mean to feel something that's hard or rough, okay? So how do we do this? This was led by my master's student. This is master's thesis actually, Samson. We're trying to bridge touch with language here, and this is the third bridge. Okay, so there is a data distribution gap, okay, between the images that typical multimodal models are trained with. So typically ImageNet is very different from the tactile sensors, tactile videos that I just showed you, okay? Those are different. So we needed to collect data for this. And so the students, collected a whole bunch of data. Here's an example of the data collection process. 70-day objects, about 400 videos, about 2,000 annotations, okay, almost 3,000 annotations. So this Kelvin here, he would press the object, also kind of twist it in order to get different kinds of tactile videos, sensations, if you will. There's a new data set now. They've been hard at work. We've increased the number of videos as well as annotations by an order of magnitude. So this is the data collection process, which is also annotated with hardness, roughness, and bumpiness. And now we've added in an evaluation suite. So these are tasks that you hope that LLM that understands touch can do. Things like, if you touch an object, can you describe it? Is it rough? Is it soft? How about property object modeling, property object matching, sorry. You give it tactile sensations and you say, these are coming from 3 different objects, can you match them, okay? So how does, and then using this kind of evaluation suite and training data, we trained a model that can recognize touch. So let me kind of briefly cover how this model works. You have a particular text that says describe the physical properties of, then here comes the tactile information. We have a symbol to represent that called text start. This is our tactile input, goes to a visual encoder into a projection module, and then finally a symbol that represents the end of the tactile information. This goes to a large language model, in our case Vicuna, which is a llama-based model, and this model then outputs some description of this tactile input. So let me kind of, the paper goes into lots of detail, lots of ablations and things like that. I'll just show you kind of zero-shot classification because this is the most fun part for me, okay? So I'm going to show you 2 tactile videos. You have a look and then you can try to guess what these things are, okay? So I'll show you A first. Okay, did you guys see that? No, I'll show you again. Okay, what do you think that is? Okay, I'll show you B. Okay, so Samson says to Octopi, given A and B, describe them. Octopi then says, after training, A feels soft, exhibits a notable roughness, and there are tiny bumps and ridges present. B feels solid and sturdy, lacks noticeable roughness, and there are no prominent bumps or ridges. So that's what it's describing. And then Samson says both are parts of toothbrush, which is likely to be the handle and which is likely to be the bristles. And then Octopi says, well, A is more likely to be the bristles and B is more likely to be handle, which is, I bet, coincides with your intuition as well, and it's correct. You can do other things, such as classify whether avocados are ripe or not. So avocados are pretty hard to tell apart whether they're ripe or not. You need to touch them. So in this case, we are asking the robot to figure out, okay, which one is the right one and put it in a bowl. And so it touches the 2 avocados. And touches the second one. Okay, this one is hard to tell from the images. At least I can't really tell which one's hard or soft. And it then describes the 2. Based on how we've trained it. And then it says, it uses now its common sense reasoning, common sense understanding of the world, that riper avocados are softer, so that's the one it's going to pick in order to put into the bin, or the bowl in this case. Okay, now Octopi is successful here. So let me finish off with some takeaways. One, I think we're just at the beginning of this. Okay, this is one of the first few works, kind of looking at how to extend LLMs with a sense of touch. But I think this is very important. It allows them to understand physical properties of objects in the world. And I think that what we've shown here is property inference helps Llama 2, in this case Vicuna, in its inference task. So you might be wondering, why did you kind of prompt the model in that way? Why didn't you just say, these are the tactile signals, they come from a toothbrush, which ones are the parts, right? Which part was what? It turns out it doesn't work so well when you do that. Maybe it's due to the base model that we're using, which is Llama 2 based. Maybe more powerful models can go direct, but at least the ones that we tried, having it describe the objects first and then doing the downstream task helped a lot. We can do zero-shot scenario inference. Performance, okay, so I'll mention it, but this is really quite exciting that, it's never seen avocados before, it's never seen these toothbrushes, yet it can perform the task. And for next steps, I think performance needs improvement. So the overall kind of accuracy for avocado, for example, ripeness classification, about 63%. So not fantastic, okay? Don't think that we can do this all the time now. There's still a lot to do. And I think that we need better data, more data, and better modules. So something I really want to improve is this tactile encoder, right? Encoding from the tactile signals to the embedding space. I think this needs quite a fair bit of improvement in order to get something good. I think that we can leverage a lot of insights that we've been building over the years in tactile robotics and putting this into our model. And I think from a scientific perspective, it's interesting to understand the nature of the different social modalities. So modalities give us redundant as well as complementary information, I think. So some things like rough and soft, some things can be described in language, some things cannot be described by language. Right? When I buy t-shirts, I don't know you guys, when I buy t-shirts, I like things that are comfortable, that feel nice. It's hard to describe these things when I go to the shop. I actually have to feel it to know which shirt I'm going to buy. And I think many people might be like that as well. So there's this kind of information that touch provides that other modalities may not. Now, since when we started this a year ago now, and I thought we would seem like the only ones, but now there's been other touch-based LLMs popping up. There's TVL from Berkeley and from Ken Goldberg and from Calendra's lab at TU Dresden and Meta. There's Unitouch from Yale. So these things are popping up. I think it's really exciting because the community is seeing that, okay, there is value in these things, so maybe let's start building them. Tactile data is hard to get, so I'm hoping that maybe we can all join forces at some point, do a RTX thing maybe and merge all this data together in order to get something more performant. Okay. So let me kind of bring you back to the big picture. Okay, I said there is 2 worlds, and what I'm working on is kind of bridging these 2 worlds, but to help people in the long run. And I think that right now with these technologies and the developments that we're seeing in the field, I think it's a nice time to rethink how we're building these robots. So how many people actually came to the debate the other day about the generative AI thing? Okay, I see some people. Okay, as you can see, I'm not that extreme, right? I don't think that Gen AI is going to eat everything. Now that's not really my stance. I think that the methods coexist. But I do think that some of the things that we found very difficult before, they may not be so difficult now. That's why I'm optimistic. This aspect of social and task and motion planning, doing this in an integrated way, seems like we can maybe try to do that now. But with current models at least, we are not there yet. We need to think about good architectures that scale with data, yet can leverage what we already know. I think we need to scientifically better understand and characterize how transfer works so that we can use the right kinds of data, we can collect the right kind of data, and we can use the right kind of models in order to get our systems as performant as possible and as safe and trustworthy as possible. Okay, so with that, let me end here. If you want to find out more, some of the stuff is on our website, or will be soon, or you can send me an email. Thank you.